Hello students, myself Dr. Divya, Assistant Professor at Department of Chemistry, Institute of Aeronautical Engineering. So today we will learn the different types of lubrications with examples and the mechanism. So with continuation with the properties, we will understand the oiliness of lubricants, then aniline and mixed aniline points, then acid number, then saponification number. These are very important properties that's to be considered before we apply any lubricant to the industrial applications. Then coming to the mechanism, we will understand what is thick film, or the other name is fluid film or hydrodynamic lubrication mechanism with example. Then thin film or boundary lubrication. This is the other type. And then extreme pressure lubrication. These are the three types of lubrication mechanisms that we are going to study. So properties, oiliness is one of the property. So it is defined as a property of lubricants by virtue of which one fluid gives lower coefficients of friction. So one fluid having low friction coefficient than another fluid of the same viscosity. So that is nothing but oiliness. Even though the viscosity is same for two different fluids, the oiliness depends on the coefficient of frictions. So it is a property of lubricant to stick onto the surface under the conditions of high speed and heavy load. So it is the ability of any fluid or lubricant to stick onto the surface when it is under high pressure and heavy load. So this is an important property in selecting the lubricant for any particular application. So for any application, it is very important to consider the oiliness of that particular lubricant. So generally what happens under the conditions of heavy and high speed and heavy load, the oil may be squeezed out because of heavy load present and running in the high speed. The squeezing out of oil takes place from the sliding surfaces and oil film may be reduced. So the thickness or the oil film that is present between these two surfaces will be reduced in thickness. So with this result, what happens? The lubrication action stops. So the lubricating property or the action stops because there is no more oil or the lubricant present between these two metal surfaces, and the metal to metal direct contact will take place. So for example, this is metal 1 and metal 2. There is lubricant in between these two metals. So if it is under high speed and heavy load, what happens? This will leak out. This will leak out from this between these two metals. So then what happens? There is no more lubricating property of that particular lubricant present because very less amount of lubrication or the oil is present between these two metals, and these metals will come in contact. So because when it come in contact, the wear and tear will take place. So it is very important to consider the oiliness of any particular lubricant before it is being applied to any application like machinery or industries. So a lubricant which does not squeeze out. So there are some lubricants that does not squeeze out from the sliding surface under the conditions mentioned before, like heavy load and high speed, maintains a continuous film. So when it is not leaking out, what happens? It will maintain a continuous film-like property, so or the film, and is known as oil having high degree of oiliness. When it is maintaining the continuous film, then it is known as that particular lubricant is known as high degree of oiliness. So normally fatty oils having high degree of oiliness. So fatty oils are nothing but that come from the vegetable source. Vegetable source fatty oils contain high degree of oiliness than lubricating oil from the petroleum source. the lubricating oils from the petroleum source. So what happens when we want to use this petroleum source lubricant oils? Then we have to mix some fatty oils from the vegetable source. So further, the degree of oiliness of lubricating oils obtained from petroleum can be improved. So the oiliness of that particular lubricant can be improved by adding little quantity of oleic acid or stearic acid. So these are the additives that are being added to the synthetic or the petroleum source lubricants to improve the oiliness of lubricants. Then the other property is the aniline and mixed aniline point. So the aniline point of an oil is defined as the minimum temperature at which equal amounts of aniline and lubricating oil are miscible. For example, if we want to add aniline to a particular lubricant, then it is important to consider the aniline point or the mixed aniline point, because there should be a phase that is forming a single phase. So when we mix aniline with the lubricant oil, there is a temperature at which it forms a single phase. So that is nothing but aniline point. So the value gives an approximation of content of aromatic compounds present in oil. So this gives an understanding of whether the aromatic compounds are present in that particular oil. So since the miscibility of aniline, which is also an aromatic compound, suggests the presence of similar compounds in the oil. So it means the lubricating oil, if at all contains aromatic compounds, will be dissolved along with aniline. So that is how it gives an interpretation of presence of aromatic compounds in particular lubricating oil. So the low aniline point is the greater is the content of the aromatic compounds. So if it is low, then it will have high organic or aromatic compounds. So that is how it is determined or interpreted. For example, this is the apparatus we use, aniline point apparatus, where we have a jacket tube. This is the jacket tube and the test tube, which is kept inside, holding it vertically. Then we take the oil inside, or the lubricant oil inside this test tube. Okay, so this is the stirrer. This is the stirrer that is kept, and a provision for thermometer. This is the thermometer where we check the temperature. So what happens when there are two different phases? This is how the separation is, but at one point it is completely miscible. So there is no separation of phases. So after some time, when we keep it away from heating, it is again separating into two different phases. So that is nothing but the lowest point where it forms miscible solution is the aniline point. So this is how we compare the aniline point with aromatic compounds that are present in particular oil used for the lubrication. Then comes the acid number. So acid number measures the level of acidity present in a lubricant called as acid number, and is also an indicator of oil serviceability. So it means if at all the oil contains or the lubricant contains some acidic property or the acidic nature, it is tested by or known by the acid number. So how is it done? It is useful in monitoring acid buildup. So it will also help in monitoring the acid that is built up in the oils due to depletion of antioxidants. So this is what when we use, for example, vegetable oils or animal oils will have antioxidants. So due to their depletion, it will convert into acids, forming acid buildup in the oil. So that will increase the acidity in the oil. So that this acid number will give an understanding where the acid number, how much is the acid number for that particular oil or the lubricant. So the oil oxidation causes acidic byproducts. So these byproducts will increase acidity level in the oil or the lubricant. So high acid levels can indicate excessive oil oxidation or depletion of oil additives, and can also lead to corrosion of internal compounds. For example, we have already studied in our previous sessions, like oxidation of presence of these oxidation property will affect the metal parts in corroding. So whenever there is excess oil oxidation taking place for that particular oil or the lubricant, it will further favor in corroding that particular metal compounds wherever it is applied in lubrication. So by monitoring the acid level, the oil can be changed. So if we really monitor the acid level by intervals or timely, the oil can be changed before any corrosion takes place. So how is this acid number determined? Take 1 gram of oil sample of the lubricant, then add 5 ml of ethanol in the conical flask and add 2 to 3 drops of phenolphthalein indicator and titrate against KOH. We are determining acid level in oil or lubricant. So we have to titrate with a base, nothing but KOH 0.1 normal KOH. So what happens? There is a color change. And that will indicate the acid number. So the calculating the acid number of that particular oil will help us in knowing whether it is having high acidic nature or levels. Therefore, we can avoid that oil and replace the oil with a new one so that no damage or corrosion takes place. So let us see what is the level of this acid property that is having. So for example, if it is having organic acids like organic acids, then it can be used for all the lubrication environments because there is not much damage going to take place. If it is like hydrochloric acid or hydrofluoric acids that are forming, then it can only be used for the chillers. Then if it is sulfuric acids, then diesel engines, and engine compressors, hydraulic systems, etc. If it is nitric, then we use for the lubrication oil can be used for gas engines or gasoline engines. Then phosphoric acid, if it is forming, then only for the mobile equipment, especially hydraulics. That is the machinery, the minute machinery that is having a slower function. So this is how we categorize the acid type and their application part. Then the other property is the saponification number. So what is saponification number? The number of milligrams of potassium hydroxide that combines with 1 gram of oil under some specific conditions. So what are these conditions? For example, saponification number will also indicate the amount of fatty saponifiable material in a compounded oil. For example, if it has oil containing triglyceride, when it reacts with KOH or the base and under heat, it forms glycerol and soap. So the ability to form soap or saponification is nothing but saponification number. So that will indicate the amount of fatty saponifiable material present in compounded oil or lubricant. The caution must be used in interpreting test results if certain substances such as sulfur compounds or halogens present in oil. For example, if any oil contains sulfur or halogen compounds ending groups, then they also react with KOH, thereby increasing the number of apparent saponification number. So that is how we have to take care. And then how the determination is done. We take lubricant or the oil and mix with excess amount of KOH and reflect for about 2 hours. Then we add phenolphthalein indicator. After adding phenolphthalein indicator, it will to pink. Turn to pink. So when it reacts with KOH, and reflexing is nothing but heating. So when we reflex with KOH, the KOH will be used of converting to soap or saponifiable material. The unused KOH is used for determining the saponification number. That is nothing but we are titrating with a HCl acid. So when we titrate with acid, the pink turns to colorless. So that is the end point. This is also called as back titration because we are titrating the unused KOH that is present in that solution or the lubricating oil when most of the KOH is already used up. So this is how we use the titration method for calculating saponification number. Then comes the mechanism of lubrication. So what really happens during the lubrication, that is whenever the lubricant is applied on the metal surfaces. So lubrication film between two contact surfaces is really thick enough and two contact surfaces are separated completely by this viscous film oil. So what happens when there is no oil or lubricant? The surface of metal 1 and metal 2 interact or rub with each other and will damage. But when there is an oil layer, the rubbing of the metal surfaces reduce and will help in smooth functioning of machinery. So at this time, what happens? Frictional force of two metal contacts are determined by viscous resistance of lubricant, which should be very small. It means that the frictional force that is present between these two metal surfaces is determined by its viscosity. The oil viscosity plays an important role here, wherein the frictional coefficient or the coefficient of friction depends on. So depending on that, there are different types of mechanisms that takes place. That is thick film, thin film, and extreme pressure. Thick film, wherein examples are greases and Vaseline we use that are applied in thick films between the surfaces. Thin film are blended mineral oils, wherein a very thin film like less than 700 angstroms is used. This is around 1000 angstroms. And extreme pressure is oil with chlorinated ester is an example, wherein additives are added to the lubricant oil so that the lubrication is increasing. So let us see in detail. So fluid film or thick film or hydrodynamic lubrication. This is the one of the type wherein it is used in the mechanism takes place in fluid lubricants. In this mechanism, what happens? Two moving or sliding surfaces are separated by a thick film of lubricant fluid. So what is the thickness? 1000 angstroms. So this is the thickness of the film or the lubricant oil or the grease that is applied between two surfaces. So it prevents the direct surface to surface contact and consequently reduce wearing and tearing of metals. So for example, bearings. So here the bearing is running. This is the metal 1 and metal 2 or the surface 1 or surface 2. Surface 1 and surface 2. So the oil, this is the lubricant oil that is applied between these two surfaces. As we see, it is thicker. So the surface is it is moving on a rolling elastic contact. So the bearing is moving smoothly because of presence of these lubricant. This is how the lubricant is applied before fitting. So the thickness is around 1000 angstroms. There is a load on one surface, applied load on one surface, and it moves very smoothly because of presence of lubricant oil. Then in this case, what happens? Mixing hydrocarbon oils and antioxidants with long chain polymer will help in maintaining the viscosity. So in order to maintain the viscosity, the hydrocarbon oils and the antioxidants are mixed, so that there is the presence of these antioxidants and hydrocarbon in the hydrocarbon oils will help in maintaining the viscosity. So this mechanism is useful in delicate and light machines like watches, clocks, guns, and scientific instruments or equipment. So these are very small parts that are in practical applications. So these lubricating oils are the mechanism, thick film mechanism can be applied in these particular applications or gadgets or any equipment. Then comes the second one, thin film or boundary lubrication. So what happens in a thin film or boundary lubrication? We'll go in detail. Then mainly the importance or the characteristics of a thin film lubrication are: it should have high viscosity index, then resistance to heat and oxidation, then good oiliness, then low pour point, then coefficient of friction between 0.05 to 0.15 centimeter per seconds. Then thickness is 20 to 30 angstroms. If you see, the thickness is very less when compared to the thick film or hydrodynamic lubrication. Then film formation is by either physisorption or chemisorption. These are the modes of mechanism that takes place, or the film formation modes during which there is thin film lubrication taking place. Then fatty acids and their soaps are used as additives to increase their lubrication property. So we will see in detail how the lubrication takes place when it is thin film. So adsorption of lubricating oils to both surfaces is by physical or chemical means. Then these adsorbed layers. Adsorption is only just physical or chemical adsorption between the two layers of metal surfaces. Then on both the metal surfaces carry applied load. Then the coefficient of friction is between 0.05 to 0.15, and distance between surfaces is to be in the order of distance of asperities, that is nothing but the hills and valleys. These are the hills and valleys that are forming when the two metals come in contact. So the distance between the surfaces, the distance between these two surfaces is nothing but the distance between these two hills and valleys. So it is directly proportional, like the distance between these two metals is defined by distance between these hills and valleys forming. So for boundary lubrication, the lubricant molecule should have what a lubricant should have: long hydrocarbon chain with polar groups. Then these polar groups will help in spreading and orientation over metal surfaces at high pressure. So these polar groups will help in spreading the oil on the metal surfaces. Spreading the oil on the metal surfaces only at the boundary. Then there is also attraction between chains and the lateral level. Then active groups should be present which form chemical linkages for the metals or other surfaces. So there should be active groups that should be present in the boundary lubrication, so that the lubricant, so that it forms the linkages with the metal or the other surfaces. So if you see, for example, this is metal and this is other metal. So there is this is the thickness. This is the thickness. Thickness is around 10 to 20 angstroms. 10 to 20 angstroms. And there is a thin film. This is less than 700 angstroms. So we are calling thin film lubrication. And this is the lubricating oil, and this is the oiliness additive. So this is nothing but polar head and its tail that is present. Polar heads, those adhere to the surface of these metals. Adhere to the surface of these metals. So what happens? This will impart some oiliness, and the shaft example is like when does this mechanism takes place? Shaft starts moving from the rest. Nothing but in bikes, if we use, there is a shaft that we are using, changing the gear system. So when it is a rest, we are changing it to the other gear system or moving condition. So in that application, we impart this boundary lubrication. So slow speed and high load and low viscosity of lubricant. So in this particular lubrication mechanism, what happens to the friction or the coefficient of friction at some particular temperature, like upon operation, with increase in the temperature, there is a decrease in the friction because of acting of the lubrication upon the metal surfaces. Then after a critical temperature, there is again a rise in the friction. This is because of decomposition or vaporization of that particular lubricant present between the metal surfaces. Then what happens during that time? The polar heads will be dissociated or moved from their original places. So that is why it decomposes or vaporizes. Decomposes or vaporizes. So after critical point, after critical temperature, after certain temperature, this is what it happens. So then there is a rise in the increase in the friction. So it is of no use further. So then what happens? This is in the case of mineral oils or vegetable oils that are present. As such, if the mineral oils or vegetable oils are applied as lubricants, then this is what the case happens. After critical temperature, there is increase in the friction again. So with this, we are understanding that after certain temperature, the friction will increase as the lubricant will lose its property. So what it really happens? It is carried out with semi-solid like grease or solid like graphite or molybdenum disulfide lubricants. And boundary lubrication is a condition where lubricant film becomes too thin to provide total separation. This is an example of train valve that is used in automobiles. So that also imparts boundary lubrication wherein very thin film of lubricant is applied. So what happens? The thin film of lubricant is adsorbed, as we have seen before. During adsorption, a weak van der Waals forces acts in holding this thin film lubricant. So it mainly operates at low speed and heavy loading or pressure, high pressures at low speed. So this forms the thin film lubrication. So examples for thin film or boundary lubrication are vegetable oils and animal oils. So glycerides of higher fatty acids and the soaps, and these oils either physically adsorb on the metal surfaces or chemically react at the metal surfaces. So although these oils possess adhesion property, although they have adhesion property, after some temperature they tends to break down, or they have the property to break down. So then what happens? Yet they tend to break down at high temperatures. So fatty acids are added to improve the oiliness. So mineral acids or vegetable oils and animal oils tends to reduce their lubricating property after certain temperature or the critical temperature. So then fatty acids are further added, or the additives are added to improve the oiliness of that particular lubricant. So graphite and molybdenum disulfide alone or oil suspension may be used. So in this, these are the type of additives or lubricants that are used in along with these, or in oil suspension, mostly used in the aircraft parts. So because they have low internal friction then can bear withstand compression and thermally stable. So if we see the particle size, the graphite particle size is 40 microns, whereas for the molybdenum disulfide it is 6 microns. And the density also is very varying. However, the melting point, if we only have to consider the melting point, it is very high for the graphite when compared to molybdenum disulfide. So these two materials can be used at high temperature applications. So with that continuation, like from boundary lubrication, we will understand how we have to apply extreme pressure lubrication. So boundary lubrication, when there is a critical temperature that is present, after that it cannot work. So in that case, we apply extreme pressure lubrication mechanism. So what happens when moving or sliding surfaces are under very high pressure and speed, a very high local temperature is attained. So it requires some materials that can operate at high temperatures. So what happens in that conditions? Liquid lubricants fail to stick. So liquid lubricants does not stick properly to the metal surfaces and decompose and eventually vaporize. So that is how the lubricant property is lost for that particular lubricant. So to avoid this, what are we doing? Special additives are added to mineral oils. So these special additives are nothing but extreme pressure additives that can withstand high temperatures. So we will see in detail. So this is the metal, two metals that are present. Metal 1, metal surface 1 and metal surface 2. So this is the lubricant present between the surfaces. So when do we use extreme pressure mechanism? The additives when are added to the mineral oil lubricants. So the additives should be chemically active groups like chloride, sulfur groups or phosphorus groups depending on the applications. Then reactive metallic surface. Reactive they will form or act will be reactive, should have the reactivity to the metal surface. Then surface free from pre-absorbed material. So the surface must be free from any absorbed material, previously absorbed material. So for example, if we see there is mineral oil we are using. So if we use mineral oil at lower temperatures, it is okay, but as the temperature increases, the friction is increasing. So it is of no use for lubrication. But what happens in the fatty acid, as we see in the boundary lubrication, what happens? There is a decrease in the friction, but it will increase after critical temperature. But when we use extreme pressure additives alone or the lubricants, extreme pressure lubricants alone, there is a constant. It is constant till the critical temperature. Just like the friction is constant, it has no work there, like it doesn't act much, but it tremendously decreases its friction after the critical temperature and maintains, and the friction goes on decreasing. So this is how the extreme pressure lubricants help. But this is in the constant range, so we doesn't want that to happen. So then what we have to do, the fatty acid is mixed with extreme pressure lubricants. Then what happens? The dark green one is the one where fatty acid is mixed with extreme pressure lubricants. So the friction reduces till the critical temperature, and further also it reduces. It means the lubrication action is going on or working smoothly. Lubrication action smoothly goes on. So there is no increase in the friction, or the coefficient of friction does not increase. So what happens when we react? This is what when the metal is reacting with some active groups like chlorine, sulfur or phosphorus, it forms Iron, for example, if it is a metal surface, iron chloride that can withstand 650 degrees centigrade. So we can use that lubricant till 650 degrees centigrade. Then iron sulfide, if it is forming, if it is reacting with sulfur group, then also it can operate high temperatures like 1100 degrees centigrade. So the coating is less shear strength, so that it is helping or favoring in lubrication action, and machinery runs smoothly. So these additives, whatever additives we are imparting or making it react with the metal surfaces, forms durable films. So it is a permanent change that is happening to the metal that is happening. So durable films on metal surfaces that can withstand high loads and temperatures. So the important additives that are used are organic compounds having chloride, sulfur or phosphorus ending groups. Then they react with metal surfaces to form metallic compounds. So when it is forming a compound, it possesses high melting point and serves as good lubricants under extreme pressures and temperatures. So like chlorides, sulfides, phosphates and many like this, forming a durable film. So if you see, this is a polar head additive. When it is added, it will be forming a soapy like film. So we will see in detail, like here you can see organic compounds containing chlorine, sulfur and phosphorus form compounds with high melting points. So examples are esters, natural and synthetic fatty acids. These are some of the examples. And in the solid materials, graphite and molybdenum disulfide are used for these purposes, and these molecules form a polar head and a insoluble or oil soluble ending or the tail. What we have seen previously is like this. This is the metal polar head and oil soluble tail. This is the polar head. So that is how it forms. It is just absorbing onto the metal surface and reacting either by the physisorption or the chemisorption taking place. If it is taking or the chemical reaction is taking place, then it forms modified metal surface. The metal surface is modified with this lubricant. So in reacting with this metal surface, these additive types form new compounds like iron chlorides, iron phosphides or iron sulfides, depending on the compound that we use. And these metals produce chemical like or slippery soapy layer that acts as a barrier to reduce friction. So forming of the soap like film will reduce the friction, wear and tear during its operation, and also eliminate damage, thereby reducing the welding purpose for any machinery. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.